Okay, if you are in the stream, please say something in the chat so I know you're there. Alright, to start us off today, let's take a look at our calendar. So this week we have normal classes, it's just a normal week. But next week is the start of Thanksgiving, and that is on Wednesday, the 25th. So really next week we only have Monday that we're going to have any class. And then when we get back from Thanksgiving break, we have Monday and Wednesday that we'll be having class. So there's kind of these 3 days there that are all broken up, and I'm actually not going to be delivering lectures on those days. Again, that is Monday the 23rd, Monday the 30th, and Wednesday the 2nd. I won't be giving lectures on those days. I'm going to give you those days to work on Hawks and get done with anything you need to complete on there. Now, that means that we're getting to the finals area of our course, and we don't have a whole lot left to cover. Really, we're just going to cover it today and tomorrow. So, let's go ahead and start in on this. Again, if you are in the stream, please say something in the chat so I can see that there are people here. So what we have been going over lately is normal distributions and taking normal distributions and finding where data is actually located within the distribution. Thank you, Jacob. So we said that with a normal distribution like this, what we're looking at is the frequency of each data point. How frequent is it? How many times does it occur? So like things over here don't occur very often, things over here also don't occur very often, but right here in the middle at the peak, this is what occurs the most often, and that is the mode. However, we know that because this is symmetrical, since both sides are the same, thank you, Juan, then this also represents the median and the mean. Okay. And what we've been doing recently is taking a value, maybe something over here, some value for x, and seeing how much data lies on one side or the other. So for instance, if we are calculating how much data is on this side, okay, what we do is we find a z-score for this area. And that z-score is x minus the mean divided by the standard deviation. So you would take whatever x value says, plug it in there, whatever mean we have, plug it in there, and then divide it by the standard deviation. That gives us a z-score that we can then look up on our z-table and find a probability for that area. In other words, what percent of the data is in this area. Okay? Now, this can actually be applied to binomial distributions as well. I don't have a good example of one, but I can kind of sketch one out for us. So if we have a binomial distribution, it's kind of like having two of these. So maybe something like this. Okay, so binomial distributions where we have two different variables that we're looking at, of course, and so we have a curve here. This is a normal curve. We have a curve here. This is also a normal curve, and both of these together represent the two aspects of our data that we're observing. So we can do very much the same thing with this that we can do with this. You know, with our z-score, finding this area, we can do something very similar here, but we have to sort of play with the numbers a little bit. So let's get an example going. Again, ultimately our goal is to get that z-score and get a value, a probability that aligns with that z-score. So typically the type of information that's going to be given to us is n, x, and p. N is the number of data points that we have in our set, of course. And for this one, I'm going to say we have 20. X is the location that we're looking at, like here. So for this one, we're going to say that x, we want the values to be greater than or equal to 8. So like if this was 8 right here, we'd be looking at the values bigger than 8. All this stuff over here. And then P is a probability. And for this one, we're going to say it's 0.25. Okay. One more thing that we're going to need in order to calculate this correctly is a Q value. But you will not be given a Q value. You're going to have to find the Q value. Well, luckily, it's ridiculously easy to find. It's just 1 minus P. So you could think about this as the probability of a particular event occurring. This is the probability of a particular event not occurring. So in this case, if we find our Q value, so again 1 minus P, so 1 minus 0.25, that's going to give us a Q value of 0.75. And now we have everything we need to start in on this problem. First of all, we need to see if our data can actually fit and approximate this binomial distribution. Okay, what I mean by that is not all data has enough width in it to be able to work here. What we're trying to do is we're taking this idea that we have for normal distributions and applying it to these. Now, if this one just isn't going to be able to fit, we'll find out pretty soon by doing n times p and n times q. So we're taking the number of data points we have and multiplying it by the probability of an event occurring. And then we're taking the number of data points we have and multiplying it by the probability of an event not occurring. Thank you, Alante. Now, if both of these are at least 5, then we're good to go. But both of them need to be at least 5. So let's plug in our numbers and see. So n is 20, p is 0.25. So 20 times 0.25 gives us exactly 5. So that's good. That one works. N again is 20. Q is 0.75. And 20 times 0.75 is 15. So that is also at least 5. So our data is going to be able to fit for this approximation. Now something else we actually just found here, N times P is also our mean. It's one of those pieces that we need for our z-score, so that's good. We've got one of our pieces. So our mean is 5. Well, another piece that we need for our z-score is standard deviation, but that's not something that's been given to us. Again, we're going to need to find that. So something we can do is N times P times Q. This will give us not standard deviation, but variance. And if you remember, variance is just standard deviation squared. So if we take the square root of this, it will give us our standard deviation. So let's go ahead and plug the numbers in. Again, N is 20. P is 0.25. Q is 0.75. So multiply all those together. And I think that's 3.75. 20 times 0.25 times 0.75. Yeah, 3.75. But again, this is not our standard deviation. This is variance. In order for us to make this into standard deviation, we need to do the square root of that. Okay, so let me find the square root of this real quick. And so that comes out to be 1.9365. This is our standard deviation. So our mean is 5. Our standard deviation is 1.9365. So now we only need one more thing for our z-score, and that's x. Well, if we were just talking about a normal distribution, this would be it. We just plug in 8 and get on with our lives. However, this is not an exact normal distribution. Again, what we're trying to do is approximate a value for a binomial distribution. So we've got to play with this a little bit because it's not quite in the right location. We need to find what is called the continuity correction factor, which is a complex sounding term, but it boils down to this. I've got a chart here that shows you what you do to find your continuity correction factor. Basically just which of these do you have? Okay, so if you look at our x, we have x is greater than or equal to 8. So we need x is greater than or equal to, and that's all the way down here at the bottom. X is greater than or equal to n. So it tells us, okay, if we have this situation, then we need to look over here. We are going to subtract 0.5 from our value. Okay? So 8 minus 0.5 is 7.5. And there's the x value we're going to use. Again, this is called continuity correction factors. You can find this on Google. And you'll need to have that, by the way. Alright, so now we have all of our pieces and parts. Again, we got our mean, we got our standard deviation, and we got our x, our corrected x. That's important. So now we just need to plug those three numbers into here. So z equals x is 7.5 minus the mean is 5 over the standard deviation, which is 1.9365, and this will give us that z value. Now, before we start calculating this, I actually want to do one more thing, and that is to sketch out what our problem looks like. Okay, so if we have a normal distribution, our mean is here at 5. And then the point that we're looking at, 7.5, would be above that. Now the last part of this is that we're looking for greater than or equal to that. So greater than, the part that is higher than that. That's this area right here. So this tells me two things. First of all, I know that my z-tables only calculate below points, not above like I need here. So once I get my z-score, I'm going to need to subtract it from, once I get my probability, I'll need to subtract it from 1. The second thing it tells me is that this is not a very big area. It's quite small, actually. So the probability I'm looking for should also be quite small. All right, so now that we have this sketched out and we know what we're looking for, let's go ahead and calculate this and see if it fits what we just sketched out. So on the top here, 7.5 minus 5 is 2.5. Divide by 1.9365, and we get a z-score of positive 1.29. I've rounded that, but that's what we get. And this is a positive z-score, so we are going to need our positive table. So let me look here. First two are 1.9, so let me find 1.2. So let me find 1.2. There it is. And then scroll over till we get to 9. And so I get 0.90147. Okay. Now that probability, if we convert that into a percent, is 90%. But remember, when we sketched this, we said we're looking for something small. So we've forgotten to do something here. Ah, yes, that's right. What we just calculated is this area back here, which obviously, yeah, that's a lot. But we're not looking for all this back here. We're just looking for the part above here, this shaded region. So we need to use not this for our answer, but 1 minus this. Okay, so let's go ahead and subtract that from 1. So 1 minus 0.90147. And that gives us a new probability of 0.09853. And if we were to convert this into a percent, of course, move that twice, that means that we have just under 10%, which is much smaller. And yeah, that looks like it'd be fit pretty well. So there's our answer. Okay, so do y'all have any questions? While y'all are thinking about that, I'm going to quickly go back over this. So again, we know how to work with normal distributions, and a binomial distribution, hopefully, is going to be just two normal distributions. Now, if that's the case, then we can do n times p and n times q to see if our data is going to fit. And as long as n times p and n times q are at least 5, then we're good to go and we can start calculating things. N times p will also give us our mean, which is one of the things that we need for our z-score. Another thing we need is the standard deviation, which we can get by multiplying n, p, and q to get the variance, take the square root of that variance, and we now have our standard deviation that we need. The last part that we need is x, which we get from looking at our x value, but we can't use this one. We need to correct it so that it more closely fits this model. So we look at our table here for our continuity correction factors, find which one we need, go ahead and subtract that or add it. Some of these add, but go ahead and add or subtract to the x value to get the new one. And then just find your z-score and make sure that you're calculating on the correct side, like this one. The first probability we got was the side we don't want. We just wanted the one on top. Okay, so it doesn't look like we have any questions, so I'm going to go ahead and move on. All right, so time for a real world example. Sorry about that. So this example that I pulled up says 62% of 12th graders attend school in a particular urban school district. If a sample of 500 12th grade children are selected, find the probability that at least 290 are actually enrolled in school. Okay, so there's a few things that it gives us here. First of all, 62% of 12th graders attend school in this particular school district. So that is a probability. If we're talking about everybody around here, 62% of them are in that school district. That is a probability. And remember, we need that probability for this. Okay, second thing it says is if we take a sample of 500 of these students, what is the probability that at least 290 of them are actually enrolled in school? Well, if we're taking a sample of 500 students, then that is our n. That is how many data points we're talking about, 500 in total. And then the last part there, what is the probability that at least 290 are actually enrolled in school? That means that x needs to be at least, or greater than or equal to, 290. Again, it's greater than or equal to because it has to be at least 290. Okay. So again, one thing that might be a good idea is to find your q, just so that we have it. So q is 1 minus p. So basically it's the opposite probability. Now it gave us our probability as a percent. We don't want it to be a percent. We always want to calculate these probabilities using decimals. So convert 62% into a decimal. That gives us 0.62. So now 1 minus 0.62 to get our q. And that gives us, let's see, 1 minus 0.62 is 3.8. I'm sorry, 0.38. Okay, so let's go ahead and start calculating things. First of all, let's make sure that things are actually going to fit for this approximation, so we need to do n times p. That's going to give us our mean anyway, so we need to do that no matter what. And then we also need to do n times q. Okay, so n times p, that's 500 times 0.62. Let's see what that is. 500 times 0.62 is 310. And then n times q, so 500 times 0.38 is 190. Okay, so good. Both of those are at least 5. That means that this will indeed fit to our approximation. So we can move on. Again, our ultimate goal is to get z equals x minus mu over sigma. So we've got our mean, it's 310. We need that standard deviation. So we need to do n times p times q. So 500 times 0.62 times 0.38. That's going to give us 117.8. But remember, this is variance, not standard deviation. We want standard deviation. So what we have to do with this to get to standard deviation is take the square root. So I'll take the square root of 117.8. Let's see, square root of that. And it gives us a standard deviation of 10.8536. Okay, so we have our mean, we have our standard deviation, now we need our x. And our x is right here, but we need to change it so that it fits the model better. So we need to go and look at our chart. This is x is greater than or equal to, so x is greater than or equal to right there. So we need to subtract 0.5. Okay, so 290 minus 0.5 is 289.5. Okay. And now we can just plug things in. So z equals 289.5 minus 500, I'm sorry, not 500, 310, divided by our standard deviation, 10.8536. And again, it's always a good idea to sketch what you're doing so that it's harder to mess up. So our mean is right here, 310. The score we're looking at is about 290. So that's under 310. And we want the things that are above that score. So that's above the score. Okay, so we should be looking for a probability that is rather large. In fact, this is most of the curve here, so we're looking at something around 90%. So let's see what we get. So the top part, 289.5 minus 310 is going to give us a negative value, so this is going to be a negative z-score, so negative 20.5, divide by 10.8536, and we get a z-score of negative 1.89. So let's look at our negative z table. See, negative 1.8, then all the way over to 9 is 0.02938. Okay. But again, this is where that sketch comes into some use. This, what we just calculated, is the area below the point. So this is just this unshaded region. We don't want that though. We want the other half. So we're going to have to subtract this from 1. So 1 minus 0.02938. 1 minus 0.02938. And that means that this area right here is represented by 0.97062, which as a percent is 97.062%. Quite a large percent, which is what we were looking for. We were looking for a large percent. So we can say that the probability that at least 290 students out of the 500 selected going to that school would be a 97, little bit over 97% probability. Okay? So I think that will probably do it for today. Again, something you should really make sure you do, find this chart online. Again, it is called the continuity correction factor chart. The website that I got it from is, actually I'll just copy this in. I can send it to y'all through the chat. So that's where I got my copy of the chart. So make sure you have that, and other than that, I think that's it. So I hope you have a great day, and I will see y'all on Wednesday.